a shock of icy water, silence so absolute it hammers your eardrums. Then out of the Antarctic blackness, something vast and clawed drifts through super-oxygenated gloom. Down here, in darkness thicker than night, cold does the unthinkable, it breeds giants. Each drop in temperature doubles the dissolved oxygen, slowing life's engines and twisting biology so isopods grow as long as baseball bats, sea spiders sprawl wider than dinner plates, and worms become ribbons of living muscle. You feel the cold shock, the pressure pressing on every hollow, the way distant echoes fold back like metal. Glowing sediments drift past, bioluminescent flakes that turn the scene surreal. But why does the cold push Antarctic creatures to terrifying size when elsewhere it shrinks life? Tonight, the true rules of polar gigantism and the limits of evolution come into focus. In the Antarctic deep, the chemistry of life bends to the cold. At temperatures near -1.8 degrees Celsius, each liter of seawater holds about 2.5 times more dissolved oxygen than the same water at room temperature. This is no minor surplus. It is a biochemical windfall. Oxygen, usually the limiting currency of animal growth, saturates the water column. The Southern Ocean becomes a reservoir where supply vastly outruns demand. For every 10-degree drop in temperature, the metabolic rate of cold-blooded creatures halves or even quarters, a relationship known as the Q10 effect. Metabolism here slows to a crawl. Respirometry experiments confirm that many of these giants, sea spiders, isopods, and amphipods, burn oxygen 5 to 10 times more slowly than relatives from warmer seas. The result is a world where animals can afford to grow, year after year, without the usual penalty of running out of breath. The oxygen solubility curve climbs steeply as the temperature falls, a silent enabler of excess. In this environment, the balance tips. Oxygen is no longer a ceiling for body size. Instead, it becomes the scaffold on which giants are built. The cold ocean acts as both a brake and a buffer, slowing the engines of life while flooding tissues with the raw material for growth. This is not merely larger gills or lungs. It is a fundamental shift in the equation of survival. Animals can invest in bulk, in storage, in elaborate morphologies, because the gas they need is everywhere and their needs are few. Yet, abundance brings consequence. The slow burn of life means that existence here is measured in decades. Growth is glacial, but relentless. The Antarctic deep is a place where patience is rewarded with mass, and where the chemistry of cold rewrites the limits of the possible. At these depths, the Antarctic cold is not the only force at work. Pressure mounts relentlessly. Every 10 meters adds another atmosphere, until even simple biochemistry must adapt or fail. Enzymes, the molecular machines that drive life, face a unique challenge here. Under crushing pressure, their active sites, the regions that bind and transform molecules, can collapse or seize, stalling vital reactions. Yet in Antarctic giants, these enzymes remain flexible, tuned for both the cold and the weight of the deep. Laboratory assays reveal that lactate dehydrogenase and ATPase from Antarctic fish and crustaceans operate efficiently at 0 degrees Celsius, even when squeezed by 200 atmospheres. This is not luck, but evolution. Subtle shifts in amino acid sequence grant these proteins a pliancy that resists pressure-induced rigidity. The cell membranes, too, are engineered for survival. In the warmth of temperate seas, membranes grow more rigid as temperatures drop, threatening to lock cells in a chemical stasis. But in Antarctic life, the lipids that make up these barriers remain fluid, even in the deep freeze. The secret lies in their composition, unsaturated fats that kink and twist, preventing the membrane from solidifying under pressure. This preserves the delicate balance of transport, signaling, and energy flow that keeps giant bodies alive in the abyss. Oxygen, abundant in every icy current, must still be captured and delivered. Here, respiratory pigments, Hemoglobin in fish and hemocyanin in crustaceans undergo their own transformation. Antarctic forms show a marked increase in oxygen affinity. Hemoglobin curves shift leftward at low temperatures, binding oxygen tightly even when pressure rises. Hemocyanin molecules, extracted from giant amphipods, hold on to oxygen with a tenacity absent in their temperate kin. These adaptations ensure that, despite the crushing weight and numbing cold, every cell receives its share of the life-giving gas. A physiologist deep in the lab describes it this way. At -2 degrees Celsius, pressure and chemistry conspire to slow everything down. Only the most flexible enzymes, the most finely tuned pigments, can keep these giants moving. A giant isopod crawls across the Antarctic seabed, its armored body stretching nearly 76 centimeters from head to tail. This is not an outlier, but a product of the abyss, an animal 50 times larger than its temperate cousins, built for endurance and survival in a world where food arrives as rare, monumental feasts. Its thick exoskeleton shields it from crushing pressure and from predators, while enormous gill plates along its underside extract oxygen from water saturated to the brink in what are effectively super-oxygenated waters. Each meal, a whale fall or a fish carcass, can sustain it for months. Inside, vast stores of lipids and glycogen fuel years of slow existence between banquets. Nearby, a swarm of giant amphipods, some over 30 centimeters long, descend on the remains. These crustaceans are both scavengers and opportunists, their translucent bodies revealing the pulsing organs within. When a food fall lands, hundreds gather in a feeding frenzy, their size granting them dominance over smaller competitors. The energy stored in their bodies allows for long migrations across the abyssal plain, always searching for the next windfall. Their numbers and size reshape the rules of who wins and who goes hungry. Drifting above, Antarctic sea spiders move with eerie calm. The largest, Colossendes megalonyx, extends its legs more than 1 meter across. Unlike most arthropods, these giants have no lungs and no gills. Oxygen seeps directly through a porous cuticle, a living membrane that becomes more perforated as the animal matures. This adaptation allows them to push the boundaries of diffusion, fueling a body that dwarfs all relatives elsewhere on Earth. Their hearts pump hemolymph through long, spindly limbs, delivering oxygen to the farthest extremities as they hunt soft-bodied prey. Threading through the sediment, ribbon worms stretch and contract, some reaching lengths of 10 meters or more. Their bodies, muscular yet gelatinous, slip between rocks and burrow deep into the mud. These predators can engulf prey nearly their own size, using a proboscis that shoots out with startling speed. In the Antarctic deep, even the worms are giants, silent architects of the benthic maze, evolving forms that seem to defy the limits of anatomy. Everywhere, the cold and pressure shape bodies into titans. In this world, size is not excess, but survival, a direct response to the chemistry of the abyss. The diversity of these invertebrate titans hints at an ecosystem where the rules of life have been rewritten and where the next encounter may reveal something stranger still. In the endless black of the Antarctic deep, bodies without bone or armor drift and pulse. Giant jellyfish, their bells spanning more than 1 meter, trailing ribbons of stinging tissue through water cold enough to numb the senses. These are not the fragile medusae of temperate seas. Here, gelatinous forms become colossal, supported by the same physics that shapes the armored giants below. Neutral buoyancy is their shield, their tissues nearly indistinguishable from the icy water, allowing them to hover for weeks while expending almost no energy. Each slow contraction of the bell moves massive volumes of water, sweeping prey into the waiting curtain of tentacles. In these super-oxygenated depths, even the simplest bodies can grow immense. Bell diameters of 80 centimeters are not rare, and some specimens glimpsed only briefly by submersibles may exceed 1.5 meters. Above the seafloor, oversized Antarctic fish drift with a different kind of grace. The Antarctic toothfish, stretching to 2 meters and weighing over 150 kilograms, is a master of the abyss. Its secret lies in a liver swollen with lipids, natural oils that make the body nearly weightless, countering the crushing pressure and allowing slow, effortless motion through the water column. The skeleton, less mineralized than those of shallow water relatives, reduces density further, a living compromise between strength and lift. To survive in water that hovers near freezing, these fish circulate antifreeze glycoproteins in their blood, keeping tissues fluid where others would freeze solid. Their metabolism, slowed by the cold, makes them patient predators, able to wait motionless for hours before striking with sudden force. Jellyfish and fish, so different in design, converge on the same solution: grow large, move slowly, endure. The cold does not demand speed or agility, but buoyancy and metabolism shape life here. In these layers, size is both weapon and armor, a means of surviving the slow-motion drama of the Antarctic abyss. An ecologist watching the silent ballet of these giants reflects, "In this ocean, the rules of buoyancy and metabolism shape creatures as much as predation or competition. The result is a parade of giants, some soft as mist, some hard as bone, all thriving in the coldest, darkest water on Earth." Descending through Antarctic waters, the ocean transforms into a vertical labyrinth of extremes. At 200 meters, the Twilight Zone begins. Here, sunlight fades to a faint blue haze, pressure mounts to 20 times that at the surface, and the temperature hovers near freezing. Sinking organic particles, marine snow, drift from above, offering food in thin, glittering streams. Giant amphipods and jellyfish patrol this dim corridor, their bodies adapted for energy efficiency and survival in the cold, super-oxygenated water. Below 1,000 meters, the midnight zone unfolds. Sunlight vanishes entirely. Pressure climbs past 100 atmospheres. The water, now black and silent, is saturated with oxygen, but food grows scarce. This is the realm of slow giants, ribbon worms, sea spiders, and deep drifting fish, each moving with deliberate calm. Bioluminescence becomes the only light, flickering from the bodies of predators and prey alike. Every movement is measured, every calorie hoarded. Evolutionary trade-offs shape form and behavior as growth trades speed for endurance and energy economy dominates life. At 4,000 meters, the abyss begins. Here, pressure exceeds 400 atmospheres, enough to crush unprotected life. The cold is absolute, the darkness total. Only the hardiest survive. Giant isopods, colossal amphipods, and ancient sea spiders, some living for decades on the sparse nutrients that reach these depths. The water, though rich in oxygen, offers almost nothing to eat. Growth is slow, lifespans stretch, and energy economy rules every adaptation. Deeper still, the Hadal zone plunges past 6,000 meters into trenches few eyes have seen. Pressures soar to over 1,000 atmospheres. Food is nearly absent, save for the rare descent of a whale carcass or the steady fall of fine sediment. In these trenches, life is a gamble against scarcity and the crushing embrace of the deep. Each zone, twilight, midnight, abyss, Hadal, marks a new frontier where cold, pressure, darkness, and chemistry sculpt the giants of Antarctica. What we call a vertical atlas is more than a map. It is a record of evolutionary trade-offs, a ledger of energy economy, and a laboratory of super-oxygenated waters that permit bodies to grow to astonishing scale. The limits of gigantism remain unknown, and strange morphologies still refuse easy explanation. In the silent, crushing dark, fear and awe sit side by side, because what Antarctica may still be hiding is both vast and unnamed. Every gram of Antarctic giant comes at a precise cost, and it brings a calculated benefit. In the deep cold, the economy of energy shifts in favor of bigness. The underlying principle is Kleiber's rule. As animals increase in mass, their metabolic rate rises, but not in direct proportion. Metabolism scales with body mass to the 3/4 power. This means that, gram for gram, a large isopod or amphipod burns less energy than a small one. The bigger the animal, the lower its mass-specific metabolic cost. In the Southern Ocean, where food is rare and meals are unpredictable, this scaling law becomes a matter of survival. Delayed maturity is the price of this bargain. Antarctic giants grow slowly, sometimes taking decades to reach full size. The payoff is immense. Larger bodies store more energy, whether as lipids in isopods or as glycogen in amphipods. When a whale carcass or a fish fall strikes the seafloor, these giants can gorge and then survive for months or even years on what they have banked. The ability to hold vast reserves shields them from long, barren stretches between feasts, a critical advantage in a world defined by scarcity. Reproduction is shaped by the same energy calculus. Large Antarctic invertebrates tend to produce fewer but larger offspring, investing heavily in each new generation. The slow pace of growth and the immense stores of energy allow them to endure and to outcompete smaller rivals and to weather the feast and famine cycles of the abyss. In the cold, the calculus of life tilts toward those who can wait the longest, grow the slowest, and store the most. Evolution rewards patience, and in that patience we find the strange, stark logic of gigantism. A whale carcass crashes onto the Antarctic abyssal plain, sending out a chemical plume that drifts for kilometers through the black water. Within 1 to 3 hours, the first giants arrive. Giant isopods, armored and relentless, swarm across the seafloor, their antennae sweeping for scent trails. Behind them, amphipods up to 30 centimeters long gather in waves, their translucent bodies pulsing with anticipation. The feeding frenzy begins as hundreds of scavengers converge, biting and shoving for position. Size is everything here. Larger isopods muscle smaller competitors aside, forming a living barricade around the carcass. The biggest individuals gorge first and longest, packing their bodies with rich lipids and glycogen. The feast is brief but absolute. In less than a day, most soft tissue vanishes beneath a swarm of armored legs and snapping mandibles. When the remains are stripped clean, the giants disperse into the darkness, each carrying a reservoir of energy. Some will not eat again for years. Laboratory fasting trials have shown Limits of Gigantism surviving over 5 years without food, their metabolism dropping to a near standstill, sustained by the colossal meals banked during these rare events. The energy stored in a single feeding can increased body mass by up to 50%, a living insurance policy against famine. For these Antarctic scavengers, survival depends on endurance, storage, and dominance. Each arrival at a carcass is a battle for future existence, where the largest bodies win the right to endure the longest stretches of hunger. In the deep, the payoff for bigness is measured not just in the moment of the feast, but in the silent, patient years that follow. Researchers call this the feast-famine dynamic, and it reshapes population structure, evolutionary trade-offs, and the global energy economy of the abyssal plain. Many questions remain about how often these mega events occur, which species can convert a single banquet into years of survival, and what unknown strategies Antarctic life still hides beneath the cold and pressure. Antarctic gigantism stands at the edge of what science can explain. Oxygen, cold, and pressure sketch the boundaries, but the details slip away. In sea spiders, cuticle pores multiply and widen as the animals grow, turning their skin into a sieve for oxygen. Yet the link between pore structure and metabolic needs remains largely unmapped. No one has charted how oxygen moves along the legs of a meter-wide pycnogonid, or how cuticle porosity shifts in the largest individuals. The chemistry of oxygen transport is even more obscure. Oxygen binding curves, those vital fingerprints of hemocyanin and hemoglobin, have been measured for only a few Antarctic species. The largest isopods, amphipods, deep-sea octopods, and fish have never had their respiratory pigments fully characterized at the pressures and temperatures where they live. Without these data, the true limits of oxygen delivery and body size are left to speculation. Pigmentation adds another layer of mystery. Some abyssal giants are nearly transparent, others deep red or purple. The reasons for these colors, whether shielding from stray light, storing trace metals, or reflecting unknown metabolic pathways, remain locked in tissue waiting for genomic and biochemical studies that have yet to begin. Most physiological data come from animals brought to the surface, altered by decompression and warmth. The Antarctic trenches, where the most extreme forms may dwell, have barely been touched by remotely operated vehicles or in situ experiments. No microelectrode has traced oxygen's journey from water to cell in a living giant at depth. The boundaries of gigantism are shaped as much by the limits of exploration as by biology itself. Each unanswered question stands as an open invitation. In the Antarctic abyss, each surge of cold and oxygen feeds the unknown. Even now, research vessels capture new giants, proof that our planet's deepest secrets still elude us. As climate shifts disrupt these super-oxygenated waters, the fate of these monsters hangs in the balance. The next colossal creature may already be drifting beneath the ice, waiting for us to descend far enough to see it. What would you want to discover down there?